I'm Adrian with 2-Point Trouble, and this is our trouble session with Duke currently recording. And today we are going to do Morley's triangle. Before we begin doing that, we need to talk about a few things. So Morley's triangle is if you take any triangle and you trisect the angles, which is to cut them into 3 equal angles, the intersection point of the lines will form an equilateral triangle. Alright, in a triangle, in a triangle ABC, if you bisect the angles, so cut them equally in half with 3 lines, they will be concurrent at a point I, which is the incenter of the triangle, and the incenter of a triangle is the center of an inscribed circle, known as the incircle. To better solve the problem, we need to know the angles inside a triangle or quadrilateral. So for all triangles, if you take the parallel line and draw another line, then using z action, or that this angle equals this angle equals this angle, will make a straight line. So all triangles have 180 degrees. And if you take a quadrilateral, you can make it 2 triangles, which adds up to a total of 360 degrees.
Alright, so now we need to prove Morley's theorem. Morley's theorem, remember, is that this triangle right here, right, is equilateral, meaning that all the angles are 60 degrees. Alright, so how will we solve this? Basically, there are many different sorts of methods to solve Morley's theorem, right? But I found a method, right, that's so easy, right, that you could teach your daughter or your grandmother. It's really simple and beautiful. Alright, let's go ahead and begin. So now, right, we assume that y is the center of this circle, okay? And it's inscribed inside the quadrilateral PTCD. So we must show that P is 280 degrees. Alright? Reason being is that we need to show that this point is the incenter of this triangle. Alright, so how will we solve this? Alright, so we have 2 arbitrary points, right? A and C, and where they meet, right, constructs an angle, right, that is equal to alpha, so angle A. And C is equal to gamma. Okay, so we already have 2 of our angles down. What we need now is P, the most important angle right here, because this will complete Morley's theorem. Okay, so in order to find P, right, we would go ahead and use this construction or this configuration, right, to try to find angle P. Alright, so we know that alpha plus beta plus gamma, right, is equal to 60 degrees, right? So this angle P is just the angle of the total triangle, right, minus the angle of each of these angles. So that gives us minus 2 alpha plus gamma. Alright. So far it looks like we can't really do anything right here, right? But we're going to use some algebraic exploits, right, to try to find what P exactly is. Alright. So I'm going to go ahead and add 0 to this term, meaning that I'm going to go ahead and add in 2 beta and subtract 2 beta. Alright, and what I'm going to go ahead and do is put this 2 beta inside this term right here. So now I will get 180 minus 2 alpha plus beta plus gamma, right, plus 2 beta. Alright, kids, where have we last seen alpha plus beta plus gamma? now we can knock off this term, right, by substituting 60 in there. So now we have 180 minus 260, right, plus 2. All right. And so now we know that 180 minus 2 times 60, which is 120, right, plus 2 beta gives us 60 plus 2 beta. All right, we have our 3 angles now. All right, now we just need to show what T is. Well, the angles that add up inside this quadrilateral, as shown earlier, has to be 360 degrees. So 360 is equal to P plus T plus C plus A. Well, we already have 3 angles that we already know. So let's go ahead and substitute them in for 60 plus 2 beta plus 2 alpha plus 2 gamma plus T. And we already found what these angles were, right? These angles were just equal to 60 plus 2 times 60 plus T, right? Which is just equal to 180 plus T. Right, this gives us that T is equal to 180, which is what we wanted to do. We wanted to prove that this quadrilateral, right, was actually a triangle, because this angle T, right, is just a straight line. So now we know that Y is an end-center, as alpha and alpha, right, are equal to each other. This line is the angle bisector, right? And similarly for all the other sides, right, we can show that X, Y, and Z are end centers, right? And by construction, we can show that this is alpha, this is beta, 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 and this is gamma as well.